In this video, we're going to be continuing on with our Unit 2.1 topic of formulae and amounts of substances, and we're going to be looking at calculations involving gases. So we're going to be starting in your notes on page number 9, and we're going to start off by talking about the molar volume of a gas. So Avogadro's law says that equal volumes of gases at the same temperature and the same pressure contain the same number of molecules. So say, for example, we had 50 centimetres cubed of chlorine gas, Cl2. That would contain X molecules. Now, we could work out how many there are, but just say for now that we have X number of molecules. If we also had, say, 50 centimetres cubed of oxygen gas, O2, how many molecules would that contain? Well, it would contain X molecules. In other words, the same number of molecules as 50 centimetres cubed of chlorine gas, so long as these gases were at the same temperature and the same pressure. So equal volumes of any gas at the same temperature and same pressure contain the same number of molecules. If we flip this around, we actually have a more useful application and one that we can use in calculations. At the same temperature and pressure, equal numbers of molecules of a gas are contained in the same volume. So using our example of chlorine and oxygen again, if we have X molecules of oxygen and we have X molecules, the same number of chlorine, those gases are going to occupy the same volume. So let's say, for example, X molecules of oxygen takes up 50 centimetres cubed of volume. Then X molecules of chlorine would also take up 50 centimetres cubed of volume. But to take this even further, we know that the number of molecules of a substance is related to the number of moles of that substance, be that solid, liquid or gas or solution. But we're focusing on gases here. So if we had, to take this application even further, if we had 1 mole of any gas, it will contain the Avogadro number of molecules, and that is 6.02 times 10 to the 23 molecules. So if we have 1 mole of any gas, it will contain the same number of molecules and therefore occupy the same volume. So let's say I had 1 mole of chlorine gas. That 1 mole of chlorine gas would contain 6.02 times 10 to the 23 molecules. That's Avogadro's number. And that gas would take up a certain volume of space, be that X dm cubed, so X decimeters cubed. And if I had 1 mole of oxygen gas, because it's 1 mole of the gas, it would contain 6.02 times 10 to the 23 molecules. And going back to this statement here, if we have the same number of molecules of a gas, they will be contained in the same volume. They will take up the same volume of space. So 1 mole of oxygen gas at the same temperature and the same pressure as the chlorine gas will also take up X decimeters cubed of volume. And what we call this volume is the molar volume. In other words, the volume of space that 1 mole of gas occupies. Now that's all quite abstract, but we'll put it together in an equation shortly. But let's look at a definition of molar gas volume to try and get our heads around what we are talking about here. So the molar gas volume is the volume of 1 mole of a gas, and it has to be a gas, not a liquid or solid, under specified conditions of temperature and pressure. So if we change the temperature or pressure, then our gases will not necessarily take up the same volume. So if we're comparing 2 gases and 1 mole of each of them, they will take up the same volume so long as the temperature and pressure are the same. And what you'll find is if that you change the pressure, you change the temperature, and then the volume that it takes up will change. And you're given an example here that 1 mole of gas at 20 degrees C and 1 atmosphere pressure takes up 24 decimeters cubed of volume. And we'll look at that in just a second. That's one example, but at different temperature and pressure conditions, that volume will be different. So it's important that you learn that definition of molar gas volume, essentially up to where it says EG there. But you also need to know the specific volume that gases take up at room temperature and pressure. And we've just used this example. If you work out the volume occupied by 1 mole of any gas at room temperature and pressure, it turns out to be very close to 24 decimeters cubed, and that's a value that you need to know. So we can make the following generalization, and essentially this is an application of the definition of molar gas volume, but just at room temperature and pressure. What we can say is that 1 mole of any gas at room temperature and pressure occupies a volume of 24 decimeters cubed. Because we know by Avogadro's law that 1 mole of any gas will contain the same number of molecules and therefore the same volume, and we know that if that temperature and pressure is room temperature and room pressure, then the volume will be 24 decimeters cubed. And as we've already said, the molar gas volume varies with temperature and pressure, and that's important to learn and be aware of, to look out for the temperature and pressure in your exam. And this is another one that is quite often quoted. Now, if it's anything other than room temperature and pressure, you will be given the molar gas volume. You don't need to learn lots of different molar gas volumes or be expected to work that out. But just for another value for reference, 1 mole of any gas at 0 degrees C, so that's not room temperature is 20 degrees C. So mole of any gas at 0 degrees C and 1 atmosphere pressure occupies a volume of 22.4. It would be good to be familiar with that volume as well, but the most important one is the one at room temperature and pressure. And it might be good to write down what room temperature is, which is 20 degrees C, and what room pressure is, which is 1 atmosphere. Okay, so the key thing to take away from this page is that 1 mole or equal moles of any gas will take up the same volume at the same temperature and the same pressure. And the most important value for you to learn is that 1 mole of any gas at room temperature and room pressure occupies a volume of 24 decimeter cubed. So we're going to now apply this to some calculations, but before we do that, let's recap on a couple of units because that's really important with these types of questions. So first of all, a reminder that 1 centimeters cubed is equal to 1 milliliter. You should also be aware that 1 decimeters cubed is equal to a litre. And so what we know then, if there's 1,000 millilitres in a litre, that means there's 1,000 centimetres in 1 decimeters cubed. That's all things that you should be familiar with from our titrations topic, for example, but that applies to volumes of gases as well. So what we learned on the previous page is that 1 mole of any gas occupies the same volume at the same temperature and pressure, and that is called the molar gas volume, that volume that it occupies. So what we know is that 1 mole of a gas occupies the molar gas volume, and we give that the symbol Vm. But let's say, for example, we have 2 moles of our gas. So 2 moles of our gas. What volume would it occupy? Well, it would occupy 2 times by our molar gas volume. So if we were using it at room temperature and pressure, we would say that 1 mole occupies 24 decimeters cubed. And so 2 moles was going to occupy 2 times by 24 decimeters cubed, which is 48 decimeters cubed. So what we can do with that is that we can create an equation to allow us to calculate the volume of a gas if we know the number of moles and we know the molar gas volume. And here it is just down below. So it says volume equals N, which is the number of moles, times by Vm, which is the molar gas volume. So N is number of moles and Vm is the molar gas volume. Now, normally the calculations, as we said, will be at room temperature and pressure. So the equation that we will use is volume equals N, or number of moles, times by the molar gas volume, which in that case is 24 at room temperature and pressure. So you can almost learn that as your equation, but you've got to remember to check the conditions and also check your units. Using this equation will give you your answer in decimeters cubed. So if this was happening at a different room temperature and pressure, so if we had different conditions, say for example 0 degrees C, then it would be n times by 22.4. But if it's anything other than room temperature, they will give you that molar gas volume in that case. So your calculations with these type of questions might be as simple as calculate the volume of a certain number of moles of a gas, and you would be simply using volume equals n times by 24 or whatever the molar gas volume is under the conditions in the question. But more often than not, there'll be a couple of steps in this. Quite often you are given the mass of a gas and asked to work out the volume, and so there's going to be 2 steps in this. So for given the mass, we need to be able to work out the volume. So what we know is that a certain number of moles will occupy a certain volume under certain conditions. So what we need to do first of all is to calculate our number of moles of gas from our mass. So let's look at worked example 1. So we're asked, what would the volume at room temperature and pressure be of 0.44 grams of carbon dioxide, CO2. So I know that this is a gas, and these questions only apply to gases. So what I'm trying to work out ultimately is the volume, and I can use my molar gas volume equation for that. But my molar gas volume equation, if you look further up the page, involves the number of moles, but I've been given the mass. So the first thing I need to do is to calculate the number of moles. How am I going to do that? Well, I simply use N equals mass over RFM. Our mass is 0.44 grams, and it's in the correct unit to use this equation. What about our RFM? Well, we've got 1 carbon, which is 12, and we have 2 oxygens, which have a mass of 16 each. That gives us an RFM of 44. So to work out the number of moles, we're doing mass over RFM, so that's 0.44 over 44. That's going to give us 0.01 moles, and you can put that into your calculator to check that. So I'd encourage you to do these calculations as we go along. Second step then of this calculation is to calculate your volume, because we have an equation which links number of moles and molar gas volume. So volume is equal to N, our number of moles, times by the molar gas volume. So our number of moles we've just worked out as 0.01 moles. Our molar gas volume, well, it depends on the conditions, but we're told that it's room temperature and pressure. So you need to know the value of this, as the molar gas volume is 24 decimeters cubed. We know that 1 mole of gas under room temperature and pressure takes up a volume of 24 decimeters cubed. Put that into your calculator and you get 0.24 decimeters cubed. Now what you can do is convert that into centimetres cubed if you wish, but that answer would be absolutely fine. But to convert to centimetres cubed, you would times by 1,000, and that would give you 240 centimetres cubed. But an answer of 0.24 decimeters cubed is absolutely fine as well. So 2 steps to these calculations. If you're given the mass of a gas and asked to calculate the volume of the gas, then first of all calculate the number of moles of gas, because we don't have an equation that links volume and mass. We have an equation that links volume and moles. So first step is calculate the number of moles by using N equals mass over RFM. Second step then is to calculate the volume by doing volume equals N times by your molar gas volume. Now you could also be asked these questions the other way around. This time you could be given the volume of your gas and be asked to calculate the mass. And apologies, I must have deleted the question in your pupil notes. So if you could write that in. So let's say, for example, we were asked to calculate the mass of 100 centimetres cubed, that's a volume, of carbon dioxide at room temperature and pressure. So here you have been given the volume, and you're asked to calculate the mass. So again, the first thing we need to do is to calculate the number of moles. That's like your intermediate step, because it's moles links with mass and links with molar gas volume. But this time we have been given the volume, so we're going to use the molar gas volume equation first of all. So if we know that volume is equal to N times by molar gas volume, this time I want to work out what number of moles is. So the number of moles is equal to the volume divided by molar gas volume. That's just a rearrangement of the equation, and you could put together an equation triangle to help you with that. Now, what you need to be careful of here is our units, because we've been given the volume in centimetres cubed, but the molar gas volume we usually use in decimeters cubed. So there's two ways of doing this. First of all, you could convert that to decimeters cubed. So 100 centimeters cubed is going to be 0.1 decimeters cubed because we have divided by 1,000. So that's option one. So in doing that, our volume is 0.1 decimeter cubed. And our molar gas volume at room temperature and pressure is 24 decimeters cubed. That would give us a value of 0.004167. It's basically 416 reoccurring, but we'll round that to 0.004167. That's the number of moles. The other way that we could do it is by doing, keep it as centimetres cubed. So that would be a volume of 100 centimetres cubed, but dividing by our molar gas volume in centimetres cubed. So if our molar gas volume is 24 decimeters cubed, then that is a volume of 24,000 centimetres cubed. Again, here we've times by 1,000 to convert from decimeters cubed into centimetres cubed. So it's up to you which way you do it. Either way, you'll get exactly the same answer. 100 divided by 24,000 again gives you 0.04167 moles. So it depends which way you'd rather do it, but you just need to make sure your volume and your molar gas volume are in the same units. Second step then is to calculate the mass. So previously our second step was calculate the volume, but this time we've been asked to do it the other way round, convert from volume into mass. So now we have our number of moles. We can calculate the number of mass by using the equation mass equals N times RFM. The number of moles we just calculated as 0.00416. It's really 416 reoccurring, and you'd be better keeping that value in your calculator and then just literally type in times by your RFM. As we worked out in the previous question, the RFM of carbon dioxide is 44. So that works out as 0.183 reoccurring, but again, just rounded off to three significant figures. So that's 0.183, and that will be in the units of grams. So you're better keeping your number of moles as that accurate number, and then just multiplied by your RFM to keep your number as accurate as possible. So this time round, again, we can convert from volume to mass by using two equations. Our molar gas volume equation, just rearranged to do number of moles equals volume over our molar gas volume, and then our mass equals N times RFM, using the number of moles in step number one. But again, just be really careful about your units with that as well. Let's do one more example really quickly together before trying some yourself. So worked example 2 asks you to calculate the volume of 0.01 grams of hydrogen at room temperature and pressure. You need to be careful about your formula of gases as well. Quite often, but not in all cases, our elements that are gases are diatomic. So the likes of our halogens, nitrogen, oxygen and hydrogen are all diatomic. So hydrogen is actually H2. So be careful with that. So we're asked to calculate the volume, we're given the mass. So first thing we need to convert to is moles. So your first step will always be number of moles, but the equation will depend on the information that you've been given. You've been given mass, so I can use the equation N equals mass over RFM. The mass is 0.01. The RFM is 2 because you have two hydrogen atoms, each with a mass of 1. Put that into your calculator and please do that along with me, and that gives you 0.005 moles. Then what you want to do is step number 2 is to then calculate your volume. How you do that is use volume equals number of moles times by the molar gas volume. So that's going to be the number of moles that we just worked out, which is 0.005 number of moles. Room temperature and pressure, so our molar gas volume is 24 decimeters cubed. Again, put that into your calculator and that works out as 0.12 decimeter cubed. And again, you can leave it at that, is absolutely fine, or you can multiply by 1,000 and that gives you your answer in centimetres cubed, which is 120 centimetres cubed. So what I'd like you to do now is to pause the video and to complete exercise 3. There's only 5 questions in this, so give these a go and show all your working out, and then I'd like you to mark your answers, which you'll find in the files section of our Teams page. So just be really careful. A couple of things. First of all, your formula. So the likes of chlorine, that's diatomic. So that's going to be Cl2. Argon is not diatomic. It's one of your noble gases. So it exists just as single atoms. So it's going to be Ar. And oxygen again is diatomic, which is O2. Number 4 is an unknown gas, so you don't need to worry about the formula of that. And nitrogen, again, it's diatomic, so it's going to be N2. So just be careful about those in your questions. You'll see that a number of questions actually involve density. So that's questions 2, 4 and 5. So just remember your equation, density equals mass over volume, or you might need to use a rearrangement of that. So you could also use your equation triangle there, where mass is on the top and density and volume are on the bottom. If you look at question 2, it seems quite vague. It says calculate the density of argon, but just to kind of start you off on that, have a think about what the mass of 1 mole would be. So really there you're thinking of what is the RFM, because remember the RFM is the mass of 1 mole in grams. Then you would think about what is the volume of 1 mole, and really you're thinking about our Avogadro's law, which is that 1 mole of any gas occupies the same volume at room temperature and pressure. So think about what that volume is, and then you can use the equation density equals mass over volume. So some of these will involve a little bit of thinking around that equation, density equals mass over volume. But try exercise 3. Give it a go, check your answers using the answers in files. And then I'd like to go through the next couple of pages, but we'll try and go through those a little bit quicker. So try exercise 3 and then continue on with this video. So once you have exercise 3 done, we're going to move on to pages 12 and 13, and we'll try and rattle through those quite quickly. So these are just a few further gas calculations. It's really just using those new equations that we've learnt with molar gas volumes and using those essentially in reacting calculations. In other words, taking an actual reaction into consideration and considering our balancing number ratio. So take a minute to have a read over these first 2 paragraphs, maybe even pause the video, have a read, and then play again for me to go through this, just so you can try and get your head around this next part of our notes. So Gay-Lussac's law states that in a reaction between gases, the volumes of the reacting gases, as long as they're measured at the same temperature and pressure, are in simple ratio to one another and to the volumes of any gaseous products. And this is essentially like what we say about a reaction in terms of the balance symbol equation, that the number of moles of our reactants and products are in a simple ratio to each other and equivalent to the balancing number ratio. And this law is actually related to the fact that when gases react, the volumes of gases in the reaction are in the same ratio as the balancing numbers in the equation for the reaction. And why is that? Well, it's because of Avogadro's law that said that equal volumes of gases under the same conditions of temperature and pressure contain the same number of particles. In other words, the same number of moles. Because remember, the number of moles is related to the number of particles by Avogadro's constants, 6.02 times 10 to the 23. So let me try and make that a little bit simpler. If we were looking at this equation that we see down below as an example, we can see that this is methane. So 1 mole of methane reacts with 2 moles of oxygen to give 1 mole of carbon dioxide and 2 moles of water. We're very used to that and using that in our reacting mass calculations. But we can apply that to volumes as well. Because what we know is that volume is equal to the number of moles times by the molar gas volume. And because this is, the molar gas volume is going to be constant at a particular temperature and pressure, then that means that the volume of a gas is proportional to the number of moles. And so if I can treat the number of moles in the ratio according to the balancing number ratio, then I can do that with volumes as well. So let's look at an example. So if I had 10 centimetres cubed volume of methane, as stated down here, that would mean it would react with, well, what's our ratio of methane to oxygen here? It's really 1 to 2. So that would react with a volume of 20 centimetres cubed. Just in the same way as if we said we had 10 moles of methane, that would react with 20 moles of oxygen because our ratio is 1 to 2. And we can treat volume the same way because of our molar gas volume equation. What would that give us then? Because our products are gases as well, and you can see that with the state symbols, we can apply it to the products as well. So again, let's think of our ratio. Ratio from methane to carbon dioxide is 1 to 1. So that's going to give us 10 centimetres cubed of carbon dioxide. And how much water am I going to get? What volume of water? Well, really it's steam because it's in the gas form. The ratio is 1 to 2 from methane to water. And so that would give us 20 centimetres cubed of our steam. So this is exactly what we would do with our mole ratio. Once we have worked out the number of moles of a reactant or product, we can bring it anywhere else in the equation according to the ratio. So we can do that with volumes as well because of Gay-Lussac's law, which is essentially derived from Avogadro's law of our molar gas volumes. So say, for example, let's use a different starting volume of methane. We would have 20 centimetres cubed reacting with 40 centimetres cubed of oxygen, because they're in a 1 to 2 ratio, to give us 20 centimetres cubed of carbon dioxide, because they're in a 1 to 1 ratio, and 40 centimetres cubed of water or steam, because they're in a 1 to 2 ratio. Just remember that you can only do this with gases. So if you have a reactant or product in there that is solid or liquid, then you can't use it to get the volume of that. The one other thing to remind you with these calculations or the application of this law is that it's true for all equations involving gases, but only applies to the volumes of gases reacting or produced and not the masses. So if you're given the masses of the gas, you need to first convert them to moles and then transfer them to another part of the equation. Whereas with volumes, you can just transfer them directly according to the balancing number ratio, and it just saves you that step of then converting to moles and converting back to volume again, because really what you would be doing is to convert to number of moles. You would be dividing by your molar gas volume, and then to convert back to volume for your other reactant or product, you would be multiplying by the molar gas volume, which is going to be the same number. So those two steps would just cancel out. So let's have a look at worked example 1. So it says here, in the following reaction, calculate the volume of gas, oxygen gas, O2, needed to produce 10 centimetres cubed of nitrogen monoxide gas, NO. So just like we would have done with our reacting mass calculations or our titration calculations, we write down the information that we know underneath the equation. So we're told that we want to produce 10 centimetres cubed of nitrogen monoxide gas, and it asks us to calculate the volume of our oxygen gas. So we would be used to converting this to moles, then using our ratio to bring it across to somewhere else, and then converting it to whatever we've been asked to work out. And you can do that, but you just don't have to, and I'll maybe show you it both ways to prove that. So really, because of Avogadro's law and Gay-Lussac's law, which is an application of that, we can just use our ratio to transfer the volume over. So let's have a look at our ratio. Moving from nitrogen monoxide to oxygen, our ratio is 4 to 5. So what we need to do with that is divide our volume by 4 and multiply by 5. So if we divide 10 by 4 and multiply by 5, put that into your calculator. Well, 10 divided by 4 is 2.5, multiplied by 5 is going to get you 12.5 centimetres cubed. And that's the question finished. It's as simple as that. And just to show you briefly, if we had used our molar gas volume equations, you can do it that way. So what we would be doing is we would calculate our number of moles of nitrogen monoxide, and we do that by N equals volume over our molar gas volume. Now, we're not told our conditions here, but let's assume that it's room temperature and pressure. So we would be doing 10 centimetres cubed over 24,000 centimetres cubed, because remember, our volumes need to be matching. Put that into your calculator, you get a 4.16 reoccurring times 10 to the minus 4. That's number of moles, so then I can bring that anywhere in the equation. Again, I would need to consider my ratio, which is 4 to 5. So again, dividing by 4, timesing by 5. That would give us 5.2083 reoccurring times 10 to the minus 4 moles of our oxygen gas. And then what we would do is work out our volume by doing volume equals N times our molar gas volume, which again would be 5.2083 times 10 to the minus 4 times by 24,000, because we would want to convert it back to centimetres cubed. And that's assuming that this is at room temperature and pressure. Put that into your calculator and it works out as exactly 12.5 centimetres cubed. So you can see doing this either way, you get exactly the same answer. And really it's because, as we were saying earlier, what we're doing here is we're dividing by 24,000. We are then using our ratio, and then we're multiplying by 24,000. So what we can do to make that a bit easier is just skip out the step of dividing and multiplying by our molar gas volume, and just instead just take into consideration our balancing number ratio. So let's have a quick look at worked example 2, which is just worded slightly differently, and we'll do a bit more practice of this type of question on Friday and next week, with just some other things added in as well. It says here, calculate the volume of carbon dioxide produced, and you can see our other volumes are in centimetres cubed, so I'll put my question mark centimetres cubed underneath my carbon dioxide. If 25 centimetres cubed of propane gas, so I'll write that underneath here, is burned completely in 200 centimetres cubed, which is in excess of oxygen. There's two parts of this question, so I'm going to write 200 centimetres cubed and excess there. Okay, and then it says calculate the volume of oxygen remaining at the end of the experiment. So that's the second part of our question, so I'll write that in blue. So that will be volume remaining. Okay. Now, it's important that they tell us that the oxygen is excess oxygen. So when I am transferring my volume over, I do not want to use the volume of oxygen because it's in excess. And if you think back to your limiting reactant calculations, we always use the lower number of moles of our reactant, because once those are used up, then the reaction will stop. No more of the other reactant can react because there's nothing else for it to react with. So we treat propane as our limiting reactant. So for this first part of the question, calculate the volume of carbon dioxide produced. Then what we use is the volume of propane. So again, as we have just seen, because we're working with gases, propane is a gas and carbon dioxide, what I'm trying to work out, is a gas. I can just use the ratio with my volumes. I don't need to convert to moles first. So let's have a look at our ratio of propane. to carbon dioxide, you can see that the ratio is 1 to 3. So essentially you're dividing by 1 and timesing by 3. So in other words, timesing by 3. So that gives me a volume of 75 centimetres cubed of carbon dioxide. That's the first part of the question done. Okay, so that's the answer to the first part of the question. Second part of the question is a little bit more complicated. It says calculate the volume of oxygen remaining at the end of the experiment. So what we need to do is work out what volume was used up in my experiment. So what will I then be left with? So again, we need to think of our ratio here. So if we have 25 centimetres cubed of propane reacting, that is in a ratio, sorry, I'll make these very curvy just to do this as the second part of the question. The ratio here is 1 to 5. So that's dividing by 1 and multiplying by 5. So what we know is, and if I just continue it down here, I'm sorry, this will be a little bit messy, is 25 times by 5 is 125 centimetres cubed of oxygen reacts. And I know that because the ratio of propane to oxygen, their reacting ratio is 1 to 5. So if we have 125 centimetres cubed reacting, but I started with 200 centimetres cubed, what do you think you should do to calculate the oxygen remaining? Well, simply, you calculate the volume of oxygen remaining by taking your starting volume, which was 200 centimetres cubed, and taking away the volume that has reacted. And you'll be left with essentially the unreacted oxygen. So 200 minus 125 is 75 centimetres cubed. So for those type of questions, just read the question carefully. Is it asking you for the volume oxygen that has reacted or the leftover oxygen? So again, those are just questions that apply Gay-Lussac's law, which just essentially says you can cut out that bit of converting to moles in between and actually just use the ratio to calculate the ratio of the volumes within a given reaction. So what I would like you to do now, just to finish off this section of the topic, is to try exercise 4. So there's just 2 questions in this, so hopefully it shouldn't take you too long. So these are calculations involving reacting gas volumes from equations. But just to say with these 2 particular examples that you are actually given the mass to start off with, or you're asked to work out the mass. So in these cases, you actually will need to convert to moles first. So in the first question, you've got 2 grams of your manganese oxide, so you would be writing 2 grams here. So remember that you cannot, as we mentioned on page 12, you cannot transfer the grams across directly. It has to either be moles or volumes of gases. Okay, so in this case you will need to work out the number of moles of manganese oxide first using N equals mass over RFM, and then bring that over to your chlorine and use your molar gas volume equation for that. And similarly with question 2, potassium nitrate is a solid, so therefore you can't transfer the volumes directly. So you will need to work out the number of moles that this volume of oxygen contains, and you use your molar gas volume equation for that, work out your number of moles. Bring that over to your potassium nitrate and then calculate the mass using mass equals N times RFM. So these are not exactly your Gay-Lussac type of questions. But again, they're thinking about how do I apply that equation that I've learnt into reacting gas or volume calculations. So give those 2 questions a go. So complete exercise 4, just those 2 questions. If you then mark your answers using the answers provided in the instructions document for today, and then upload a photo of your marked work to the assignment on Teams. And if you do that by Thursday afternoon at 3:30, just the end of the school day, just so that I can then check that by Friday's live lesson. As always, please just get in touch if there's any questions that you have.